Welcome to our Parasitology lecture. Today, we are going to explore a creature that completely redefines everything you thought you knew about parasites. When we hear the word parasite, we usually think of microscopic amoebas, tiny ticks, or tapeworms hiding in contaminated water. But nature is full of incredible surprises. What if I told you that a parasite could be a fully grown vertebrate animal with fins, glowing skin, and razor-sharp teeth? In this session, we will dive into the fascinating world of the cookiecutter shark, a tiny marine predator that sneaks up on massive whales, takes a perfectly round scoop of flesh, and swims away without killing its host. Let us begin our journey into the deep ocean. Now that we have introduced our topic, let us rethink what a parasite actually is. Traditionally, in zoology, we study parasites as lower invertebrates, organisms that live inside a host's intestines or attach to their skin, like leeches or fleas. However, the cookiecutter shark challenges this boundary. It is a fully developed vertebrate, a small species of dogfish shark, that has evolved a highly specialized parasitic lifestyle. It roams the deep ocean and feeds on the tissue of much larger, living animals. Because it takes a quick meal and leaves the host alive, it acts as a marine ectoparasite. This proves that the parasitic strategy is incredibly diverse and not at all restricted to simple, lower life forms. Building on this idea of a vertebrate parasite, let us look at its specific biology. Scientifically known as Eisistius brasiliensis, this creature is formally classified as a micropredator. Unlike apex predators, such as great white sharks, that hunt to kill and consume their prey entirely, this small shark only wants a piece of the pie. It has a sleek, cigar-shaped body that allows it to move stealthily through the water. But its most remarkable adaptation is its mouth. It possesses highly specialized suctorial lips. When it approaches a host, it presses these lips against the skin to create a powerful, airtight vacuum seal, anchoring itself firmly to the much larger animal before it begins to feed. Once the shark is firmly attached, how exactly does it extract its meal? This brings us to its incredible bite mechanism. After creating that vacuum seal, the shark deploys its highly modified lower teeth, which are arranged like a continuous, sharp bandsaw. But it does not just bite down and pull. Instead, the shark twists its entire body in a rapid circular motion. This spinning action allows the teeth to slice cleanly through the thick blubber and muscle of the host. The result is that it scoops out a perfectly round plug of meat, leaving behind a deep, crater-like wound. It literally looks as though someone took a cookie cutter to the side of a whale, which is exactly how it got its name. To truly understand this process, let us visualize the bite mechanism in action. On your screen is a cross-sectional diagram showing exactly how the cookiecutter shark feeds. Notice the blue area at the mouth. This represents the vacuum seal formed by the suctorial lips against the host's skin. Just below that, you can see the specialized bandsaw-like lower teeth digging into the tissue. The curved arrow around the shark illustrates the twisting motion of its body, which acts like a drill. Finally, look at the host tissue block. You can clearly see the cylindrical crater wound left behind after the flesh is scooped out. This geometric precision is what allows us to mathematically model the bite, as we will see shortly. Before we move into the mathematics of the bite, we must understand the ecological footprint of this parasite. The cookiecutter shark does not target small fish. It goes after the giants of the ocean. It feeds on sperm whales, dolphins, and even apex predators like great white sharks. Because it is a micropredator, it does not kill these massive hosts immediately. Instead, it leaves permanent crater-like draining scars across their bodies. This creates a chronic, long-term drain on the host's energy reserves. Furthermore, the deep, open wounds left behind in the ocean water expose the host to severe secondary bacterial infections, which can ultimately be far more dangerous than the bite itself.
Fascinatingly, the impact of the cookie-cutter shark extends far beyond marine biology and directly into human engineering. These sharks hunt by detecting electrical signals and silhouettes, which means they sometimes mistake human-made equipment for marine animals. During the Cold War, the United States Navy was baffled when their nuclear submarines returned with mysterious, perfectly round holes in their rubber sonar domes. It turned out to be cookie-cutter sharks. They also bit into and severed deep-sea telecommunication cables, causing millions of dollars in damage and communication blackouts. This bizarre biological interference actually forced naval engineers to redesign their equipment and develop tough fiberglass protective coatings to stop the tiny sharks.
Having seen the physical and engineering damage these bites cause, let us look at how biologists mathematically quantify the wound. Because of the shark's unique circular biting mechanism, we can model the stolen chunk of flesh as a perfect geometric cylinder. The formula for the volume of a cylinder is V equals pi times r squared times d. Here, V represents the total volume of the flesh plug removed. The symbol R stands for the radius of the bite, which is exactly half of the total diameter. Finally, D represents the depth of the bite into the blubber. Notice that the radius is squared in this equation. This means that if the radius of the shark's bite increases even slightly, the volume of flesh removed increases exponentially, resulting in a massively larger meal for the parasite.
Let us apply this formula to a real-world scenario. Imagine a marine biologist examines a fresh wound on a bottlenose dolphin. The wound has a diameter of 6 centimeters and a depth of 3 centimeters. We need to find the volume of flesh consumed. First, we must find the radius by dividing the diameter by 2, which gives us 3 centimeters. Next, we substitute our known values into the volume formula. We replace the radius with 3 and the depth with 3. Following the order of operations, we square the radius first to get 9, and then multiply by the depth of 3 to get 27. Finally, multiplying by pi gives us approximately 84.82 cubic centimeters. This means the tiny shark extracted nearly 85 grams of nutrient-rich blubber in just seconds. That was just a single bite. But what happens when a host is attacked dozens of times over its life? To estimate the total biomass lost, we first calculate the total volume by multiplying the number of bite scars by the average volume of a single bite. Once we have that total volume, we convert it into biological weight using the density formula. Mass equals density, represented by the Greek letter rho, multiplied by the total volume. Here, m is the total mass lost, and rho is the density of the blubber. If the density of the tissue is high, the physical mass lost by the whale will be significantly greater, draining more of its vital energy reserves over time. Let us see this total biomass formula in action with a concrete ecological scenario. Researchers find a stranded sperm whale with exactly 50 cookie-cutter shark bite scars. The average volume of each bite is 60 cubic centimeters, and the density of whale blubber is 0.9 grams per cubic centimeter. First, we find the total volume by multiplying 50 scars by 60 cubic centimeters, giving us a total empty volume of 3,000 cubic centimeters.
Next, we multiply this volume by the density of 0.9 to find the mass, which gives us 2,700 grams. Finally, we divide by 1,000 to convert this into kilograms. The final answer is 2.7 kilograms. This means the whale has lost nearly 3 kilograms of vital insulating blubber to these tiny parasites, perfectly illustrating the chronic toll micropredators take on their hosts. We have reached the end of our journey, so let us review the key takeaways. First, the cookie-cutter shark proves that parasitism is incredibly diverse. Even a vertebrate apex predator can evolve into a highly specialized marine ectoparasite. Second, its unique biology, using a vacuum seal and saw-like teeth, allows it to extract perfect cylindrical plugs of flesh without killing its host. Third, by using mathematical modeling, we can accurately quantify the massive biomass and energy loss these tiny sharks inflict on ocean giants. Finally, their relentless biting mechanism impacts not just marine ecosystems, but human deep-sea engineering as well. You have now mastered the biology and mathematics of one of nature's most fascinating parasites. Great work!